Big G is, I would say, the black sheep of the fundamental constants, and it describes the strength of gravity. The force of gravity is very, very weak, but it's there. So to measure in the laboratory is very, very difficult because the force is small and there's a large background from this, what we call little g, from the gravitational field of the Earth. Big G is one of the numbers that has the largest uncertainties, so we don't know it really well. Because if you look at all the numbers that people have measured over, let's say, the last 50 years, there's a lot of scatter, so the numbers don't agree. When you look in the textbook and you see the Big G value, is this number plus minus this uncertainty? A lot of the work is in the plus minus the uncertainty. Well, the first measurement of Big G in the laboratory was done by Henry Cavendish in 1798. So he used what's called a torsion balance, and we still have a torsion balance here. So this is the tool of the trade. It works like this. Imagine you have a very, very thin wire, and at the end of the wire, you have a little dumbbell. So now you bring two larger balls next to the dumbbell, and they make a small, little, tiny torque on it. So the small balls want to move towards the large balls. And so the little dumbbell deflects. So you can measure a little deflection. Now you move the big balls on the other side, and you measure the opposite deflection. It's awe-inspiring. I mean, it is just amazing that you can change the trajectory of a microscopic object of this by moving the mass on the outside. I mean, it's unbelievable. When we started at NIST about 10 years ago, we didn't want to make a new experiment because the data set, as I said, is already inconsistent and is ugly and dirty. So we said how about we take an existing experiment and repeat it? The experiment is named the BIPM experiment. So the BIPM is the Office of Weights and Measure, and this is sort of the world's metrology office where all metrology is coordinated. In the last 50 years, there have been a little bit more than a dozen measurements. I think this is one of the most important tenets of science, that an experiment should be repeatable. Otherwise, what I'm doing is not science. It might as well be gambling or playing the lottery. Originally, in this honeymoon phase, you think, oh my God, in 2 years I have a number, this will be great, this will be a walk in the park. And then you realize, oh my God, this is life-sucking. It is difficult. Nothing works. You really want to give up. I sometimes call my boss and say, this experiment is not an experiment, it's a random number generator. You know, think about it, it's a love-hate relationship that you enter with such an experiment eventually. I think the biggest problem in humans is that we want to go where we think the solution is, and I didn't want to do that at all. Then the best guardrails against this is doing a measurement blind. So that means you ask a colleague or you ask somebody else to introduce somewhere a little bit of an offset that you don't know, and they wrote spice down in a little envelope and they kept it in the desk drawer for all that time. And I didn't notice, so I calculated with this fake number, so I could never look at my Big G value that I measure and the literature to make sure it was the right number, because I did not want to stop when the number was right. I wanted to stop when I thought the whole data set that I have is self-consistent. And at some point I thought, okay, now it looks that the data set is self-consistent, so we are ready to open up that envelope. And that was a very stressful time, because when I did all my calculation, the Big G value that I calculated was really, really super high. And I thought, oh my God, this is such a high number. I must have been done something wrong. So I was really miserable. I was going, oh my God. But then when they opened the envelope.
Okay. R equals minus.
Yes.
6.5 times 10 to the minus 4.
And sure enough, it brought the number down to where it ought to be. So that was a big relief.
It is.
Oh my God.
Gravity is, for me, one of the most fascinating subjects. So we live in this fabric of space-time that's all around us. And if you put a heavy mass in there, then the space-time deflects, it bends, it has a different shape, it stretches. And the stretchiness of space-time is linked back to the gravitational constant. There is a true value of Big G that's hidden from all of us. And all we can do is probe the universe, and we get, a number that is, related to the true value, but it has our uncertainties and our errors. This is the problem, but I think it's a fundamental constant, so it does not change with space or with time. So if you measure it on Alpha Centauri 1 million years from now, it will still be the same number. We just don't know it, or we are incapable of measuring it that precisely. But it's there.